Neural networks are revolutionizing the field of artificial intelligence. They are powerful tools inspired by the human brain. These networks can learn from data to perform complex tasks. Examples include image recognition, natural language processing, and even playing games. Neural networks are becoming increasingly important in our daily lives. They power applications we use every day. With their ability to learn and adapt, neural networks hold immense potential for the future. The MNIST dataset is a classic example used in machine learning. It consists of thousands of handwritten digits from 0 to 9. Each digit is represented as a 28 by 28 pixel image. This dataset serves as a benchmark for training and testing image recognition algorithms. The MNIST dataset allows researchers to test new algorithms. It is a simple yet effective way to evaluate how well a neural network can recognize patterns. The insights gained from MNIST can then be applied to more complex image recognition tasks. A neural network is made up of interconnected layers of neurons. These layers process information to make predictions. The first layer is the input layer, which receives the raw data. In the case of MNIST, the input layer would have 784 neurons, one for each pixel in the image. The hidden layers perform computations and extract features from the data. The number of hidden layers and neurons in each layer can vary. Finally, the output layer provides the network's prediction. For MNIST, the output layer would have 10 neurons, one for each digit. Each neuron in a neural network applies an activation function to its input. The activation function introduces nonlinearity into the network. This nonlinearity is crucial for the network to learn complex patterns. Without activation functions, the network would be a simple linear model. It would not be able to capture the complexities of real-world data. Some common activation functions include sigmoid, ReLU, and TAN. Each function has its own properties and is suitable for different tasks. Section 5, Gradient Descent, Finding the Optimal Solution. So, gradient descent is an optimization algorithm that's used to train neural networks. The main goal here is to find the optimal set of weights and biases that minimize the network's error. This error, well, it's quantified by something called a cost function. The cost function measures the difference between the network's predictions and the actual values. Now, gradient descent works by iteratively adjusting the weights and biases in the direction that reduces the cost function. This process continues until eventually the network converges to a minimum point. Section 6. The role of multivariable calculus. Multivariable calculus plays a crucial role in understanding gradient descent. The gradient of a function points in the direction of the steepest ascent. In gradient descent, we are interested in finding the direction of the steepest descent, which is the negative of the gradient. By calculating the gradient of the cost function, we can determine how to adjust the weights and biases to reduce the error. This process involves partial derivatives, which measure the rate of change of the cost function with respect to each weight and bias. Section 7. Overcoming challenges. Local minima and overfitting. Training neural networks comes with its challenges. One challenge is the presence of local minima in the cost function. Gradient descent can get stuck in a local minimum, preventing it from finding the global minimum. Another challenge is overfitting, where the network becomes too specialized to the training data and fails to generalize to new data. Techniques like regularization and dropout are used to prevent overfitting. Section 8. Resources for further exploration. For those interested in diving deeper into neural networks, there are excellent resources available. Michael Nielsen's book, Neural Networks and Deep Learning, provides a comprehensive introduction to the field. Chris Oller's blog offers insightful visualizations and explanations of complex concepts. And of course, my own YouTube channel, 3 Blue 1 Brown, explores mathematical ideas in an intuitive and engaging way. Section 9. The future of neural networks. Neural networks are rapidly evolving. Researchers are constantly developing new architectures and training algorithms. These advancements are expanding the capabilities of neural networks and opening up new possibilities in various fields. From self-driving cars to personalized medicine, neural networks are poised to revolutionize the way we live and work. As we continue to unlock the potential of these powerful tools, the future of neural networks seems incredibly bright.